this video we're going to take a look at how long it takes us to find some sort of value in some sort of collection. And so let's imagine we have a collection. If you're a programming person, you can think of this as an array. Ooh boy, that doesn't look anything like an array. Alright, trying again to draw a bunch of boxes. Here we go. So if you're a programming person, think of this as an array or a list. If you're not a programming person, because clearly there are apparently two types of people in the world, just think of it as this is a collection of boxes, and maybe they're sort of cubby holes or something, and those boxes have numbers, so we'll number these in our traditional programming way of starting with box 0, 1, 2, 3, 4, 5, 6, and we have 7 boxes total. And I want to know, does a particular, let's say each of these boxes hides a number, and I want to know, does any of them hide, sure, we'll keep them as numbers. Does any of those boxes hide the number 582? Does 582 appear in one of those boxes? So how could I determine that? Well, I would look in a box, and I'd see if it's 582. And we could go in no particular order. Is it in box 0? Nope. How about box 4? Nope. How about box 2? Oop, there's 582. Then, of course, I would stop as soon as I find it. But I think instead of going in an arbitrary order, if we were to program this, we would probably find it easiest to just tell the computer, start with box 0. If you find 582 in it, you're done. Stop. Otherwise, try the next box, box 1, then try box 2, and keep going until you find 582. So, for example, let's actually see that in practice. We'll look in box 0, and it turns out box 0 contains 76. That's not 582. So we look in box 1. And box 1, we'll open it up, and it contains 823, and that's not 582, so we keep looking. Then we look in box 3, and it contains 582, and that does match 582. What are the odds? And therefore, yes, indeed, I found the value. So one possible scenario, in fact, let's give a name to this. This algorithm is called sequential search. We're searching for a value, and we're doing it sequentially. We're starting at one end and searching through my collection. We might also call it linear search, as it's sometimes called, because we're searching in a line linearly, and it's going to turn out the fact that we're searching in a line is going to have something to do with the time it takes to solve this problem. And let's look at the different possible, the sort of best case, worst case, and the sort of expected or average case. Let's see if I can be consistent here. What is the best case scenario here? Best case is we open box 0, and there it is, 582. It's our very first box we try. So 582 is in the first box. And notice that the time it takes me to look in the first box does not depend on how many boxes I have. I could have thousands of boxes and still get lucky and find the value in the first box. Therefore, in the best case scenario, we say that the time, let's see if we can do this in such a way that we're not going to run out of room so quickly. We'll spread out all of these thoughts here. You may hear some honking outside. I have an angry neighbor apparently. Let's see, 582 in the first box. Finding a value in the first box, getting lucky, does not depend on the number of boxes. Therefore, we'll say the time does not depend on number of boxes, and that means that we say it runs in constant time. Constant time. And if you're familiar with something called big O notation, you'll know that constant time means we express it as big O of 1. If you're not familiar with that, don't worry about it. Just get the idea that the best case scenario is that the time does not depend on the number of boxes because we find the value right away. What's the worst case scenario? You might think maybe the worst case is we look through the collection, the list, the array, and we try every single box until we get to the very last one where we find 582. So it's in the last box might be the worst case. In last box. Alternatively, and maybe even worse depending on how we look at it, it's in no box. We check every single box, and once we've tried them all, we frown and cry because 582 wasn't in any of those boxes. We really needed 582. It was very important to us. So the worst case scenario is that the time, we have to check all the boxes. And when we, go back. check all boxes. And when we check all boxes, that means the time is proportional to number of boxes, which in our fancy lingo we would say runs in linear time. And if you're familiar with big O notation, that means we would write it as big O of n, where n is the number of boxes. Meaning if we have twice as many boxes, and I think this is really the key insight, if we have twice as many boxes, it's going to take us twice as long in the worst case to get to that last box, or to discover that the value isn't in any box. Okay, now, that's the best case and the worst case scenario. What's the more typical scenario? When do I expect, how many boxes do I expect to open on average in order to find this value? And there's a couple ways we could look at that. It kind of depends on, if we know that the value is in there somewhere, then on average we might expect to check half the boxes. In this case, I guess that would be 3.5 boxes, right? On average we would expect to check half the boxes. But if there were twice as many boxes, if instead of 7 boxes we had 14, we would expect to have to check twice as many of them on average. And of course there's the possibility it's not even in there, so it could be even worse. But I think the key idea here is that even if I know 582 is in one of those boxes, then I expect to have to look in about half of them before I find it. And if there are twice as many boxes, I'll have to look at twice as many, right? If there are 7 boxes, I'd expect to look at 3.5 of them on average. If there are 14 boxes, I'd expect to look at 7 on average. If there's 100 boxes, I'd expect to look at 50 on average, if I know for sure that 582 is one of those values. And therefore, I'm going to check half the boxes. Half the boxes clearly depends on the total number of boxes, so again, time proportional to the number of boxes, and again, it's linear time, and we say it's big O of n, if you're familiar with big O notation. So, all of this is to say something that might have been blatantly obvious to us at the beginning. If you have to look for a value in a bunch of boxes, the time it takes you to find that value is going to depend on how many boxes you have, and it's going to be proportional to the number of boxes, right? Twice as many boxes, and it will probably take you twice as long to find the value. And there's only one situation where that's not true, and that's what if you always get lucky and it's always the first box you look in which case we say that the time is constant. Now the question is, what if we give you hints? What if instead of telling you yes or no, does that box contain 582? What if we told you some more information? Like, oh, that box doesn't contain 582, but if there's any box that does, it would be somewhere to the left, or 582 is somewhere to the right of the box you just looked in. How does having those hints change the problem? Let's take a look at that scenario. So we'll just erase these values, and we'll look in a box. Let's say we look in box 2, and we check, is this 582? And we get the answer no, but that if 582 appears somewhere, it's somewhere to the right. So let's try another box. Let's try box 5. And we look in box 5 and we find the answer is no, 582 isn't there. But if it is somewhere, it's somewhere to the left. And so now we've narrowed it down to only 2 boxes. That wasn't true before. Before, after looking in 2 boxes and not finding it, 582 could still be in one of the remaining 5 boxes. Right? But here, I've checked 2 boxes and I've already narrowed it down, so I know there's only 2 places it could possibly be. And so if we look here and find that 582 is here, we can celebrate. If we don't find 582 there, maybe we'll find no, and if 582 does exist, it's somewhere to the right. What does that tell us? It tells us 582 isn't there. So, looking in just 3 boxes in this scenario, we determined there is no 582. Now, it should strike you that if we knew we had these hints that were going to tell us go left or go right, that we've done something kind of silly by checking box 2 first. What would be the best box to check first? Box 3, right? Because as soon as we check box 3, if the answer is no, we'll immediately have narrowed down the problem from 7 possible boxes. Let's say the value is on the left, if it's there at all. We've immediately narrowed down the problem from 7 possible boxes to 3. What box should we check next? We should check box 1. And if we look in box 1 and it's not there and we find it's to the right, then now we've narrowed down the problem. whether it was originally 7 boxes to 3 boxes to now just 1 box could possibly contain the value. So it seems like we're narrowing it down very, very quickly by using these hints. Now in real life, are we really going to have, do we really expect scenarios where we might look in a box and get a hint as to where the value might be? For the answer to that, check out the next video.